Hello, everyone. Welcome to join today's TVM Unity Open Development meeting. We have three topics today. We'll see if we can have all of them today. First up, Lucian will talk about the Slim. Following that, if our schedule permits, I'll be walking you through the relaxed heterogeneous execution implementation. Stephen will lead the discussion about the data flow block extraction. Hey, Lucian, please take it away.
Sure, thanks. Can you see my screen?
Yes.
Cool. How do I? Hi everyone, Happy New Year. Welcome to the first development meeting in 2024. And I'm Le Shenjing from OctoML. Today, I would like to share Slim with you. First, I'd like to say thank you to Junru Yaxin for the great work on Slim. And the goal of Slim is to make compilation and quantization agile. And to achieve this goal, we designed a brand new PyTorch style API for TVM and did a lot of reflecting on MLCM. Let's see what Slim brings to the table. The first highlight of Slim is Slim can boost our productivities. Allow me to share a personal experience to you first. Last October, I undertook a variant of GPT-2 in the old floor, and it took me 6 days to complete model definition. And in that week, I spent most of time figuring out what is an module and how do I get the shape or even get the D type of the tensor. And it's very suffering. And in the end, the model definition takes more than 700 lines. And unfortunately, I tested the model and the model failed on the first run since we do not have good debugging tools. And I spent another 4 days on checking the correctness issue. Finally, I find I need to make sure the D type of MATMON output in float 33. And introducing quantization in old floor is also not easy. You have to be careful with parameter manager, and because if you modify it without consideration, you may break the entire pipeline. And to ensure others don't face similar challenges again, we designed and developed Slim. Last month, I contributed Phi2 to MLCLM, and thanks to Slim, I implemented Phi2 in just one afternoon, and thanks to Slim, Slim has a PyTorch style interface like an module and tensor. I reused most of the code from Hugging Face Phi2 definition. And the rotary embedding and KV cache in Slim is neatly wrapped up, so I can call it directly. It turns out Phi2 with Slim is under 300 lines, much better than the old floor. And you may know the llama.py in old floor is more than 1,000 lines, and it's very heavy. Let's get back to the Phi. While the first run of Phi2 didn't work well, but it only took me 2 hours to debug it. Similar to debugging PyTorch codes, I inserted some print statement into certain layers. Then I compare the hidden states between my model and the Hugging Face model. I can see the whole process is very smooth and seamless, and I'm sure it will benefit all the users and the developers. Slim doesn't just enhance the productivities, it also boosts our model's performance. Here is our benchmark on long contests, 16K performance of Slim against the old MLC and flash attention to. As you can see, Slim brings 61 percentage to 85 percentage end-to-end speed up, and it's up to 120 percentage faster in decoding. As we know, flash attention is heavily optimized on profiling. So as you can see, Slim is still faster than the old MLC plus flash attention 2. Without Slim, it's extremely hard to bring these performant kernels into our workflow, like the CUDA kernels in Flash Infer. If we want to do that in the old flow, we may need to add a lot of hacks into our code base, and it may break a lot of functionalities. I think it's not good for our development. Slim also works well with Disco in multi-GPU settings. We provided out-of-box tensor parallelism sharding strategy interface. Several days ago, we added Mixtra multi-GPU support, which only took around 10 lines of code. Here is some numbers on Disco plus Slim. We outperform some established benchmark like VRM, like llama.cpp, like X llama over 1400%.
Hello, sir.
Uh,
Steven has a question.
oh,
Uh,
go ahead.
Sorry to
yeah,
interrupt.
I think you might have answered it, Leshong. Thank you. Yeah, my question. So for the performance improvements you've cited, so is it fair to say with Slim, are you using better kernels already, or does it just make it easier to throw in more optimizations? I guess where do these gains come from is my question.
I think the gain is from the better kernels in Flash Infer. But it's easier for us to integrate such kernels into our framework with Slim.
Okay, I see. So the speed ups, so Slim made it easier for you to use better kernels that you already had access to. Okay, thank you.
Yeah.
Can we say, sorry, I have another question. Can we say Slim, if MLC plus Flash Infer, can we say Slim has a similar performance as that one? MLC plus Flash Infer.
We do not have old flow MLC
I
plus
see.
Flash
I see.
Infer.
Got it. Thank you.
No worries. Do you have any questions?
That's it.
Cool. So Slim is also makes it possible to bring in more features like more quantization algorithms. Now we support FT quantization and AWQ quantization. We also support more model architectures like Microsoft Phi2 and Mixtron. And the batch serving just got merged last week, and we will see it soon. And in the future, we will also introduce more models with Slim, like ASR model Whisper, like TTS model Viz. Now let me show you how to chat with large language model with Slim or run the benchmark. Here are some simple instructions. To optimize user experience, Junru has quantized a list of model weights and uploaded the quantized weight to Hugging Face so that users could easily download the models and deployment them. Let's have a chat with the new CLA with Llama 2 first. Let me see. Okay. It will download the weight, quantize the weight from Hugging Face, and it will show show what weight is downloaded, which shard is downloaded. And after a few seconds, the weight got downloaded, and we will compile the model on the fly. There is a lot of logging. Okay, after the download, it will show the memory usage, and let's have a chat. And there are some new features, like we can set some parameters in chat config, like temperature, like stop words. For example, we can set temperatures here. And we can set max generation length. For example, if we limit it to 10 words, and there is a logging shows we override some parameters. Then we have another round of chat. As you can see, the output of LM is llama is very short, since we have set the max gen length to 10, and we can set it back. Yes, that works well. And in the new chat CLI, we also support multi-line inputs. For example, hi. Yeah. So there are some new features, and we can do benchmark with similar chassis with similar CI. And we could also we also support multi GPU chat with overrides tensor parameters equals 2. And if you are a developer and you would like to compile the model from scratch, we also provide a set of instructions. Like the first step is generate MLC chat config. The second step is compile the model. The third step is convert the weight and quantize the weight based on the quantization arguments. And with quantize the weight and the compiled model libs, we could use the chat CLI to chat with it. Okay, let's talk about the system design. Like I mentioned, like I mentioned in the beginning, defining a model is very hard in the old flow. It requires TVM knowledge, and debugging a model is also very painful because we do not have a print function, and we also don't have a JIT. So every time we need to test the model, we have to manually compile the model and prepare the inputs as TVM and the array. To fix these two pain points, Slim offers a PyTorch style API. Here I use llama model definition in Slim as an example. I showed the attention layers in llama. In PyTorch, the layers of neural networks typically inherent from an module. In Slim, we provide the same interface module, which is a pure Python object with identical APIs to PyTorch modules such as state dict named parameters. And inside the attention module, we defined a linear and 2 KV catches. In Slim, we wrap KV catch up as an effort and allow users to create directly. And we have two interface, view and append, to view the elements or to add new elements to the KV catch. In the order flow, you may need to write a lot of callback func to create a catch or query the catch. And let's go to the forward function. Here I'd like to highlight some new features. First is it's calling the forward function of a sub linear module, and for here we call QKV projection forward function to get the projected output QKV, and here we provide two out of box rotary embedding and attention with flush infer. And in the blue box is KV catch usage. We append the K and V into KV catch and view the total sequence long element out of the KV catch. And in the attention function, we have I'd like to highlight the touch style operators. We created convenient shortcuts for basic tensor operators like add. For example, here x plus y is equal to op dot add x y. And we also supplies like multiply and maximums. And now we can also directly get the d-type and the shape of the tensor, which is very useful for compile time debugging. In the order flow, it may requires us to use tensor structure infer d-type. The type conversion is also available with as type. And the last feature is chain operators. Unlike the order flow, where we need a lot of emit around each operators. Now chain operator is more seamless and easy to understand. After we finished the model definition, how do we put the NNDAO module into TVM compilation flow? We have a conn function named as export TVM. And the export TVM function would export the NNDAO module to TVM IR module, and it will also returns a set of parameters. In this example, we create a llama, then we use export TVM to export to IR module and a list of parameters, and we can also get a dictionary named parameters which contains parameter names and d types. And you may notice there is an argument spec. What is it? It's a data structure defined which relax functions are going to export. For example, in this spec, the output mode would have three functions: prefill, decode, softmax with temperature. And the values in the spec defines the input parameters of relax function. Let's take a prefill as example. Function prefill will have two inputs. Inputs one is named as inputs, and it's a tensor with shape, batch size, and sequence length. And the second parameter, total sequence length, is an integer. Note that the sequence length is a symbolic var, so which means inputs is a dynamic shape tensor. So that we can provide a function name and its input signature, so that we can define a bit, so that we can completely define a relax function. But for now, only tensor, tuple, and integers are supported as inputs. We will support more data types later. And I can give you detailed examples to better explain the calling convention. On the top left side is a linear, it's a layer definition. We defined a layer, and there is a linear inside the layer, and there is also a KV catch. In the forward function, we would call the linear first, and call the reshape, call the print, and also we would interact with KV catch, and we will return the result y. It's only for the demo use, so do not care about its meaning. And on the right side is spec, which means we want to export the forward function, and its inputs is tensor x, and another inputs total sequence length is an int. Then we call layer dot export TVM with this spec, and it will transfer the end module into a TVM IR module. The input IR module will have a specific order. The function inputs comes first, like x and total sequence long comes first. X is a tensor, and total sequence long is a shape, and it's stored in a shape, and then comes the effects, including KV catch and including IO effect. And IO effect is the backbone of the print function we will introduce later. As in the last part of the inputs is parameters. The layer has two parameters, layer weights and linear bias. The output of the IR module contains the output of the forward function here y, and the updated KV cache and updated IO effect. And after we talk about the model definition, let's talk about the debugging experience. We provide two per layer model debugging tools. One is print function, the other one is JIT. The print function would print the tensor shape and the tensor D type here, and also the runtime value to the screen. It's very useful when we want to compare the hidden states between our implementation and Hugging Face implements. And another way is another tool is JIT. JIT is a tool that helps us convert indoor module to a touch module, and touch module is a touch in touch out module, which means the model takes touch dot tensor as input and touch dot tensor as output. I will introduce it more. I will introduce the details in the next page. And on the left hand side is it's a JIT example, and on the right hand side is it's a JIT workflow. The JIT workflow first step is to convert the indoor module into IR module. The second step is to convert parameters. The third step is to compile the indoor module and feed it to the VM so that we can get the runtime module. And in the end, we will wrap the runtime module into touch module. And let me introduce more about the touch module. The inputs of touch module would just as I said is touch dot tensor, and the first step of touch module is to convert these inputs into TVM data structures. We would call touch to TVM. It will convert touch tensor to TVM ND arrays, convert int into shape tuples. It also will recursive convert a tuple into a list of ND array or list of ND array, list of shape tuple. And these inputs will be fed into the TVM runtime module. For example, here we feed into the forward function, and the output will typically it will be TVM ND array. In some cases, it could be a tuple of TVM ND array, and then we will use TVM to touch to convert TVM ND array into TVM tensor and convert tuple into a tuple of touch tensor, and so that we achieve the touch in and touch out. So there is no need for users to convert inputs from
Seems we've lost connection.
Yeah, we can wait Lawson to join.
Well, I hope he knows that he lost the connection.
Maybe I can ping him. Give me 1 second.
Ah, here he is. Hello, Lasheng. We lost you at some point midway through explaining how torch modules work.
After
the-
the touch module, yeah.
I see. Give me a second. Let me find my points. Give me a second. Can you see my screen?
Yeah.
Okay. The next topic is PyTorch style quantization. There are more and more quantization algorithms nowadays, and it's important if we can support new quantization algorithms as soon as possible. So there are many good repos on GitHub that help user to quantize their model and do the deployment. Like For example, auto AWQ and auto GPTQ. I abstract the core logic of these two models. Auto GPTQ would iterate through all the layers of the model and converts the linear into a new quantized linear, and auto AWQ would iterate layers of the model and collect all the linears to collect all the linears and convert linears to WQ linear GM. And the key is that we need to have a tool to iterate through the model and convert some specific layer into quantized layer. So can we do such things in n-DOM module? The answer is yes. We have n-DOM mutator. We designed the mutator that works through the module and applies the transformation to different level. And the mutator is in pure Python and doesn't require any TVM knowledge. You could, for example, you could override if you want to do a transpose to all the parameters, you could override visit parameters. If you want to change the order of the modules, you can override the visit function. Here is a simple example of a group quantization mutator. The mutator overrides visit module function, and it will visit through all the modules. If the module is linear, it will replace it with a group quantized linear. If it's an embedding layer, it will replace it with quantized embedding. If there are other layers like conv1D, it will just skip and just jump into the next level. And with this mutator, we could convert a model into quantized model in one line, like mutator.visit model. And we also support FT quantization, and here is its mutator. The mutator converts linear into FT quantized linear and embedding into group quantized embedding. In the old flow, applying FT quantization would block a lot of things, but Slim makes the quantization implementation constant and unit testable. And also many thanks to Yaxin for bringing FT quantization into Slim. And the integration of Disco in Slim is also very neat. For example, we could set tensor pattern sharding strategy in model definition within 20 lines. The key function is shard single dim. It means it will shard a tensor along a single dimension, and the shard strategy we defined will be stored in the attributes of parameters. While in the compilation, we will dump all the shard strategies into model metadata, and in the load time, the loader will pass the model metadata and get the shard strategy of each parameters, and the loader will shard the tensors based on the shard strategy. This is on the left-hand side is Llama tensor parallelism implementation, and a quick callback. I did a presentation about Disco a few months ago, and I introduced how to do tensor parallel on two linear on two layer MLP, and we would shard the first matrix along the special dim, which means dim 0, and shard the second impure weight along the reduction dim, which means dim 1. So following this methodology, we could shard GitHub we could shard the llama MLP's GitHub projection along dim 0, and shard the down projection along dim 1. Slim also provided multi-GPU support operators like CCL broadcast from worker 0 and CCL or reduce. The last topic is about OP integration. Slim supports constant cross-layer OP integration. In Mixtron, Junru and Hongyi wrote many performance kernels in TIR and tensor expression to support MOE, like MOE Matmon GMV, it's in TIR, and like MOE sum is in tensor expression. Without Slim integration, TIR and the TOPs in one system and brings them to a same level is very hard. And another example is flushing. Zhao wrote a lot of performant CUDA kernels, and it's very important to long context performance. And with Slim, we could embed the flashing first seamlessly into our attention OP so that user can use it out of box. And that's the introduction to Slim. And thanks, folks, for listening.
Thank you. It's a very, very detailed presentation.
Thank you, Leshan.
Here, listen.
I hope you can folks can try on Slim.
Yeah,
It's
so one thing I
very-
think worthwhile talking about is actually in the CLI, I remember like Rehan and others have this ability to be able to find fully UTF-8 token. So like for emoji streaming. So maybe you want to check if we have that text streamer implementation correctly. Yeah.
I see.
Yeah, I think that
Got
is
it.
one catch that, but it's great that we can migrate to the new one. I
see.
think there
I
are only
will do
a
a
few
check.
final pieces, and we can fully duplicate the original one and start to use SlimFlow. Yeah.
Yeah, sounds good.
Leshang, would you be so kind as to send me a copy of these slides if you're willing to? I'd like to include them with the
Sure.
notes. Thank you.
No problem.
Listen, I have one question, a small question actually. You mentioned that we have some synthetic, I would say it's like a synthetic sugar. For example, X plus Y to represent relax at AX Y. How do you implement that in the A module? I'm just curious about this.
I see.
I think it's very helpful for us to touch this code from
I
the
see.
from. It's very
Let me find the
helpful.
source code. I think it's not so. Give me a llama. Let's find a tensor. We override the add function in for tensor. For X plus Y, actually it's X dot add
see. I see.
Why?
Got it. You guys
So it will
rewrite
convert
this.
into op.add.
Got it. Interesting. Very helpful. Thank you.
Yeah. Thank you. Any other questions?
It sounds like there aren't questions right now. I think we do have time to move on to the next agenda item.
Cool.
Thank you once again, Lashunga. That was an excellent presentation, very detailed, and I'm glad we have a recording of it. Young, would you like to give a few words about, if you think we have enough time, would you like to give a few words about distributed or heterogeneous operations in Relax?
Yeah, maybe I can quickly go through that part. And let me see. Yeah. Seems for that relaxed heterogeneous execution, for this topic, because we already discussed this design aspects during our previous Unity Open development meeting before a few months ago. So today's focus just will be more practical. I will take you guys through end-to-end demo, and we'll walk you guys through the related code very quickly because time is limited. Let me share my screen. Can you guys see my screen?
Yes.
Okay.
Yes.
Yeah. Here is the end-to-end demo example for heterogeneous execution. In this demo, we have a very simple relax function that in the R module for sure. And we have a simple relax function. In this function, we just have three operators in this data flow block. The first operator is matmore. The second is to-v device. The third one is matmore again. The first matmore we can see here, LV1 variable was allocated with LLVM. For the heterogeneous design, if we allocated the variable as we allocated this guy as the V device to the tensor structure info, we will know this variable is supposed to be located on the LVM device. It could be a CPU device. We can see that then LV1 is on LLVM. Then the second operator is to copy this variable LV0 to CUDA. It's a copy to copy this tensor from device to device to another device. Then the third operator is to do matmore, and we already allocated this variable is on CUDA, so we know this matmore happens on CUDA. So this is the simple example. Let me show you guys the code here. Let me actually compare it. Maybe I can run it again. After the user code, we will run. We apply a realize V device path to. We will apply this path to propagate the virtual device across the L module. Previously, you can see this guy X, Y. This is inputs for the function. X, Y are not allocated. But after we apply realized V device, you can see X here is allocated to be, the V device information is allocated, Y is also allocated, Z is also allocated. Z is on CUDA. You can see here, we do the matmore on LVM, a second matmore on CUDA. You can see here, this is the lowered VM executable text. So I just show you what it look like in the backend. You can see here, after the matmore, we have the 2D device will copy the matmore. You can see the first matmore here. The first false register is the output for the matmore. Then we will copy the register's value to the destination register 5. Then the 5 will be used for the following calculation. This is the unintended demo. For the relaxed heterogeneity design, we have several operators. One operator is a 2V device. In the 2V device, you can explicitly indicate the runtime to the relax to copy a tensor to some specific device as you specified. We also have a hint on device operator to help you to allocate your to help you to hint that which device the tensor is supposed to be located on. For the hint on device, I have another example here. For example, in the data flow block, you can see we do not allocate the Y because you can see Y here. Y is a tensor 2 plus 3 and float 32. But Y is not allocated by the V device. V device is not allocated. Then you can use a hint on device to tell the backend to tell relax Y is supposed to be on CPU. So we can do that. We will, after we apply the realized V device, the realized V device will try to fill the related V device into the Y and allocate the V device to the location and remove the hint on device for our following on passes. This is the 2 operator. Maybe you guys are interested in how we do the copy, the transfer of data from one device to another device. Actually, what we did is we introduced the built-in packed func, VM built-in packed func, to do this copy. If we detect the tensor is on different tensor type, we will do the copy to copy that tensor to our target device. Then we can get that. Then we will have that for our following computation. I would mention a few changes for the end-to-end case. Actually, we changed the relax build behavior a little bit. It's different from relay, actually. You can see here in relax build, we do not, we change the target as optional. So that means for the, let me see. Here, the relax build, in the relax build, the target is optional. That means if we have, for our IR module, if we have a bunch of target devices you will do some copy, you do a bunch of things on specific target, and some other subgraph on different targets. Then what we can do is we do not need to provide a specific target list to the relax build. During the building and during the lowering, we will get this target information from the R module directly. Because we can, after we apply the realize V device, we suppose all this kind of things will be propagated across the R module. Then we can get this information from the module and also the target as well. So we don't need to specify it. Then we can get this kind of end-to-end model test case work. Actually, in the test case, we have multi-CPU, and I have multi-CPU, multi-GPU, and GPU plus CPU kind of test case here. If you guys are interested, you can check it out. Yeah, we still have 4 minutes for QA. Let me know if you have any questions.
Thanks, Young, for going through the highlights. Do I understand correctly? So what? I'm sorry if I misunderstood. If you do specify a target and you have virtual devices given in the module, what happens? Is the specified target, is that just used as a default?
Actually, for that case, I think the target in the R module will be used. You specify the target for this case. I think it will. In the current implementation, if you specify target as well, I think it will raise the error. If not, I will think I'll change it.
Okay, that's good to know. So I have a couple of questions. This was very helpful actually in getting the big picture on how this works. I'm wondering, so why does hint on device, why does that need to be an operator? Like, as opposed to just having a user, put it into the struct info, or just having the user, or using or using matchcast, for example. Is there a specific reason it needed to be an operator?
I think it has having an operator hint on device will help us to change. For example, if we want to change the whole some part of the R to be executed on some device. If we have a hint on device, we can easily just change the hint on device part and do not touch other nodes in the R module. Then we can easily modify everything. I think if we manually annotate the V device information in the tensor structure info, I think it works as well. But if you want to, if you change the V device for a subgraph, then probably you have to. There are a bunch of all these things are in the module, so maybe you were lost. I think it's helpful for the user friend the debugging kind of things, I think.
Okay, this is interesting. Yeah, this is good to think about. I'm not saying I have an answer now, but it might be good, especially where we're about to run out of time. But yeah, I think this might be kind of some unnecessary duplication of functionality, right? Because we already have matchcast for forcing types for things like that. So I'm a little bit, I'm wondering whether we need another operator to do something that's already handled by the struct info system. It's worth further thought. Related, okay, I had another question. Oh yes, realize V device. Do you think realize V device should be just part of normalization? Because normalization, we do check, we check struct info during normalization, and if the V device is part of the struct info, should realize V device, should that just be included as something we do during normalization?
Currently, the realize V device is not part of the normalization. because the normalizer currently are doing some forward propagation, but for the realized V device, I introduced some backward propagation. For example, if we allocated a var, we can backward propagate the var backward to the inputs to the function. So that's why I didn't add it to the normalizer. I think normalizer still do some V device propagation, but just for some forward propagation. For the backward propagation, if it happens, then we will need to use realized V device pens.
Okay, does this create a problem, like a follow-up? Does this create a problem then? Users then they would have to think about when to call realize V device, right? Like if you have a pass that messes with V devices, you should probably call it. That means I don't know. This is why I think maybe it's worth bundling it with the normalizer, because you would need to tell when it's time to call it again.
I'm not sure if we can introduce it added to the pipeline, but we can probably discuss it if time allows. For I think
Yeah.
I think one option is we can introduce this realized V device to our pipeline. If we introduce it to the normalizer, probably it will introduce some overhead because we do not need to do this kind of backward propagation for the block builder, because the block builder relies on the normalizer. So that means the TVM script, a bunch of things will call into that.
Oh man, that is a hairy issue.
Yes.
We could keep it separate, just always call it between passes. You're right. So we are over time. It's worth thinking about. I think clearly there's more to discuss. But this was a great intro. So I guess we could pick up the discussion in the next session. Because I had also if you recall from our discussion, there were some spec questions related to this. Definitely worth discussing with the group. So I think this discussion will probably continue. What do you say?
Sure, that makes sense.
All right, then. Well, since we are at time, I guess we will wrap up here. Thank you, everybody, for attending. The item I put on the agenda will also have to be deferred, but this was great. Thank you, Lusheng, again for the presentation on Slim. That was wonderful. And Young, thank you for giving an overview of heterogeneous computation. Also, a big change, long-awaited change to the language. Please send your notes if you can. I like including them with the meeting minutes if I can. No rush on that, but it would be helpful. Thank you, everybody.
Thank you,
Thank you.
Lusheng. Thank you. Yeah.
Thank you, folks.
Thank you.